Hi there. I would like to show you a simple and efficient way to calculate boundary conditions. They do require that you know the action of your system. But if you do, then it's very easy to use this method. And I'll show you using 3 examples. The first one is a spring hanging in the ceiling at a fixed point, and we have a density rho, mass density of the spring, and an elasticity mu, and we have placed a mass on the spring. First we shut off gravitation, so the spring is hanging in a relaxed state. Then it has length L, so it goes from 0 to L. And if we set it swinging, let's just turn on gravitation, then some extension will occur and we count downwards positive. That may be counterintuitive, but it was simpler for me this time. Now, the action, it's the integration of the Lagrangian, which is the kinetic energy of the spring, plus the kinetic energy of the mass. So y was the extension, and the derivative with respect to t is the velocity. And then minus the potential energy, and usually it's minus, this half shouldn't be there, that's a mistake. Rho, the gravitational constant, times the height, but y goes downwards, so it's plus. And the potential energy of the mass at A, and then the potential energy of the spring. The modern way to do variational calculus, and when I say modern, I mean what mathematicians do. They work on this guy, not with an alpha though, and then try to make s of y plus phi minus s of y to approximate it with a linear function of phi. That might be a bit complicated, so I found a method that I feel quite comfortable about it, so I would like to show it to you. So we just expand this expression, y, s evaluated y plus, and then a little change in the direction of phi. And when we do that, we get a lot of terms from the squares that we have to expand. The first term we have here, it just gives this, of course. And then we differentiate with respect to alpha, vanishes, gives this, and gives alpha rho phi t squared. Then we set alpha to 0, meaning we only get this term. So now you should be able to write up the directional derivative. I've done it here. This we have from here. This gives rho g phi. Glad I forgot the 1/2 here. This gives mu yz phi z. This needs to be integrated over the entire spring. And then we have the mass. This is in itself a linear function, or linear functional of phi, but we need to write it as an operator on phi itself by taking an integral and multiplying by phi and then integrate over the spring. So we can write the operator. And we need to perform partial integration here, here, and here. There are no problem with these because we expect the temporal derivatives to be continuous or even differentiable all over, so no problem. But this might be a problem. Is it reasonable to believe that the yz, the z derivative, is continuous across this border? Well, if you think about Newton's law, it's not. But why not just try and see what happens? We'll do that later. Now, we split up this integral going from 0 to a and a to L and performing the partial integration. First, from 0 we get the value a, this times phi at a minus the same at 0, and then the partial integration. And the same here at L minus the value at a and the partial integration. We need to see yz is at a from the negative side and here from the positive side. These two we put together to delta yz at a. So this is what we get. So taking all the terms together, this is what we get. And we need to write it all as an integration over dz. So the way to do it is to let this stand as it is and then multiply the rest with a delta function at z equals a. We call it delta a. That's this term and this term and this term. This term, of course, is at L, so that must be multiplied with a delta function at L. At an extremum, the derivative of s should vanish. That means this vanishes, and this vanishes. The first one is the wave equation. Thank you. The second part is the boundary condition at the mass. And the third, the boundary condition at the end. And of course you immediately recognize it as Newton's second law at any point. Newton's second law used on the mass m. And this can be interpreted as Newton's second law as well. The force at the end is the mass of the end, which is 0 times its acceleration, which is finite, giving 0. So there's nothing special about the boundary conditions. They are exactly what you should expect. But that's what I wanted to show with this example, that they are relatively easy to compute, and it's a very safe way of doing it, and they give the right result. I wanted to comment on what happened if you thought that, well, maybe yz is continuous across the boundary. Then this term would be missing, and the equation one gets for a is that it just falls down by the force of gravity. Then one might think, okay, maybe it's not reasonable to think that the derivative is constant across the boundary. If you already wanted to say, okay, I like this method, let me try and use it, you might put a discontinuity in rho at some point, say a instead of being a mass, suddenly it got heavier, and discontinuity at the elasticity at some point B, and then go through and see what boundary conditions come out. And I can assure you, you'll get the expected ones, but it's nice to go through the motions. Now, this method with the directional derivative, it doesn't prove that the action is differentiable. But as physicists, we don't want to prove it's differentiable. We just want to find the differential or the derivative. So that's why I like this method. We don't prove it's differentiable. We just find the derivative. The next example is an electric field in two dielectric media with linear dielectricity, or permittivity, sorry. So we have one permittivity for Z negative and another for Z positive, what I've indicated here. I follow the, I've taken the example from this book of Reitz and Milford. You can see I have a cheap paperback second edition, but it's a very good book, and I studied the foundations of electromagnetic theory in my second year of physics, and it was very, very good. Learning everything from the very basic. So it's a good method. So when I make a new derivation of the boundary condition, which is in the beginning of the book, then it's not to say that the book should follow this. It should do exactly as it does, using the fundamental physics it's based on, just using that. But I just wanted to show that we can get the boundary conditions for the electromagnetic field using this method as well. And as an example, I'll just do it for the electric field. Now, the action, the energy of the field minus the, we have a charge distribution as well, I see, and then a surface charge between the two dielectrics. So we compute the directional derivative. You know the drill by now. It gives nabla u times nabla psi. We take the directional derivative in the direction of psi, and psi times rho and psi times sigma. These are volume integrals, and this is a surface integral. We need to apply partial integration to this part. So we split it. It's only the set integration that's interesting. The other are easy. So we split it up from minus infinity to naught and naught to infinity. And take the one from minus infinity vanishes, from naught from the negative side and the positive side. And then we combine the two here. And these, of course, give the divergence of epsilon times the divergence of u. And this epsilon is that's actually two different values. I should have written so epsilon and dv we have to put on each, we have to use it two different values here. I should have made that clear from the notation. And then we get the surface integral, which has a delta function to it, and the volume charge that has not. So here's the volume charge and here's the surface. Oh, they're both at z equals naught. So we get a boundary condition. First, the divergence of the displacement equals rho. And next, a boundary condition about the displacement is equal to the surface. The normal, as said, the normal is equal to the surface, or the discrepancy in the normal is equal to the surface charge. And in the book, it mentions this one, which we didn't get. That was surprising, but there's a good reason for it. And that's because it follows simply because we derive the field from a potential. So that shouldn't come as a boundary condition, it comes as a mathematical consequence. Here you are. Using this method, you can derive the boundary conditions for the electromagnetic field when going from one media to another, as well the electric as the magnetic potential, and therefore by the fields, and with discontinuity in the permittivity as well as in the permeability. So there you have a challenge. The last example of this video will be the relativistic Schrodinger field. Later in the series, we will use this method in the direct field when it encounters a discontinuous potential. But today, I'll just show the method when we are dealing with the relativistic Schrodinger field. In the books, it always says it's reasonable to believe that the derivative is continuous across the border. And with today's knowledge, I agree it's reasonable to believe. A lot of examples have been computed where the potential rises rather steeply, more and more steeply, and apparently some kind of convergence has been found that shows that, all right, the derivative seems to be continuous across the border. I'll show that it can actually be computed if we say, well, it's reasonable to believe it might not be continuous. Let's see what we get. The same method, we perform first, a few comments on the way I write the Lagrangian, or the action. It might be different from what you're used to seeing. I use another unit for psi. I know it's 1 divided by square root length or whatever. But this one should have units of energy per volume, so that one integrates over space-time, one gets exactly unit energy time, joule second. What I like about this is that we can read out the charge density immediately. And of course, differentiating with respect to geometry gives the what's that called? The stress energy tensor immediately, showing that the energy density will be positive always. So this nonsense about negative frequencies giving negative energy, that was just misunderstandings of the early attempts to handle these fields based on the non-relativistic Schrodinger field, of course. I think the right way is to start with the relativistic, because there we have general relativity to help us interpret the energy and momentum, and Noether's theorem to give us, well, that as well, and then also the charge current density. course this enters the charge current density as well. Well, leave that for the moment. So we say, let's see what happens if the field is discontinuous across the boundary z equals naught. So first, the directional derivative, and we have to write it in a symmetric form, and that's a complication that arises because the fields are complex functions on the Minkowski or whatever space we are using on space-time. So we need to have a symmetric guy to get a real result. So we need to perform to get rid of the derivatives here and here, and then hopefully we'll get something that gives a symmetric result. This, of course, is already symmetric, and what you would expect here is that 1/2 vanishes and we just get all this times psi, and that's what we get because this already has the form something times phi plus phi times something, and that something is psi, and 1/2 we have there. So this part times psi is exactly the derivative as expected. We perform the partial integration, and I won't read it. You can see it. It's what we have done before. And this is the only term that comes. This does not give a derivative with respect to z, because only the dt term enters. So if g is diagonal, then it's only the derivative with respect to time that enters here. And that means that we get the usual part of the Klein-Gordon equation, and then this condition. And that simply gives the delta psi z times the delta function z equals naught. And that means that that must vanish as well. So this part will give the Klein-Gordon equation, and this part shows that the derivative across the boundary is continuous.